Well, Happy New Year, and welcome to this first lecture of 2011. It's a mathematically very propitious day, as you will have noticed. It's 11/1/11. So if you have nothing better to do, you can factorize this and work out the continued fraction expansion to which it approximates, and all those interesting things, analogous to how you used to work out the prime factorization of hymn numbers when you sat in church as a child. It's the acid test of the budding mathematician. Well, today we're going to talk about some uses of irrationality, but we're going to focus upon paper sizes, which you might think sounds rather peculiar, rather odd. We're going to look at why we've developed the paper size system that we have, why Xerox machines work better with that system, why you would be mad to do anything with paper or Xerox machines in America, and then we're going to look at some of the medieval counterparts of these modern problems of paper sizing and the golden ratio. Well, the problem of paper size is, you probably realise that we deal a lot with papers which have funny labels like A3, A4, maybe if you're really exotic, B1, B2, and even the C series of papers. So what do these labels mean? Well, to get a grasp of this, we're going to need to know about one interesting number, and that number is the square root of 2, and this number famously is an irrational number, and that fact was discovered by the ancient Greeks long, long ago. It was known supposedly to the Pythagoreans, and there are stories and legends that the first person to discover it was regarded as an enemy of the people and thrown into the sea because he had unveiled something that was indeed irrational and therefore dangerous to the world of thought. Well, what does all that mean? Well, a rational number is one that you can represent as the ratio of two whole numbers, two integers. So if that number was 2/3 or 1/2, by construction it's a rational number. And this famous proof from ancient Greece demonstrates that the square root of 2, the number which you get if you make a right-angled triangle with two sides of length 1 and 1, then Pythagoras' theorem tells you that the length of the hypotenuse is the square root of 1 squared plus 1 squared, which is the square root of 2. That this number cannot be written as the ratio of two whole numbers. So how does that proof work? Well, it's a classic example of a proof by contradiction. You assume that the result is true, deduce a logical contradiction, therefore you can conclude that your original assumption was false. So the way it works is that we start by assuming then that there are two integers with no common divisor. Okay, so they're in their fraction in its lowest terms, like 1/2, not one like 2/4. And then we work out the consequences of that. So if we were to square this formula, we would have that p squared is equal to twice q squared. So that means that p squared is an even number. It's twice something that's a whole number. Well, that means, bit of thought, that p must be an even number as well. Because the only way that you can get an even number is to multiply an even number by an even number, or an even number by an odd number. So p must be even if p squared is even. So this means that p is twice some other number. We'll call it n, and if we put that back in here, we have that 4n squared is 2q squared, so q squared is 2n squared, so q squared is an even number, and so by the same argument, q must be an even number. So we've proved that both p and q have to be even numbers, so they're both divisible by 2, so our original assumption that p and q had no common divisor was incorrect. So we have a contradiction with that initial assumption. So it is not possible to write the square root of 2 as p divided by q with p and q having no common divisors. As a result, the square root of 2 was termed an irrational number. Okay? And you find this proof here in one of the books of Euclid, although we know from other writings it was known far, far earlier. So why is this number interesting? Well, if you look at modern paper sizes, we have the problem of what's called an aspect ratio with paper, that we want to be able to deal with different sizes of paper in a way that is simple and convenient. So suppose that you start here with one large sheet of paper, and the height of this long side is 2, and we'll allow the other short side to have a length r. And we're going to see if there's an interesting r. Well, first of all, rotate it round, so it's the other way round, it's horizontal. Now, suppose we wanted to cut this piece of paper in half. Okay, down the middle, we would then have two pieces which had a height h, but which each had a width 1. And so the ratio of the height to the width of the small pieces is r divided by 1, whereas for the big piece, the height divided by the width is 2 divided by r. Well, if we want these to be the same, to be in the same ratio, okay, we want r divided by 1 to be 2 over r squared is 2, and r is the square root of 2. So this ratio here is called the aspect ratio, and you can see immediately how this picture here is manifested in the relationship between A3 and A4 paper. So that if you have a piece of A3 paper, you divide it in half in this way, you end up with the two pieces of A4 where we have this same ratio of 1 to root 2 to 2 for the height against the width. If you were interested in your business or whatever you were doing, perhaps in dividing sheets of paper into 3, okay, that this is what you needed to do a lot, you could see how you would change this argument, that what you would end up wanting to do would be to have r squared was equal to 3, and you would find it very convenient to work with an aspect ratio of square root of 3. Well, paper sizes have used this A size format, this square root of 2 scaling ratio, again and again. So a sheet of A0 paper, here, we'll look at the actual size in a moment, is this large rectangle here. If you slice it in half, you will have two sheets of A1. If you slice the A1 in half in the other direction, you will have an A2. If you cut in half in the other direction, you'll have A3, A4, A5, and you can keep on going for as long as you want. Here's the same picture again, the actual measurements in metric scale going down a little further. If you work in the paper business or you're ordering paper, you might wonder about these funny numbers here. How accurate are they in practice? You know, how carefully could you machine and make your photocopier or your computer paper tray? How wrong might the papers be? And if you look at the rules for the industry, you'll find that up to about 15 centimetres size, you're allowed to make things to an accuracy plus or minus 1.5 millimetres. It goes to 2 millimetres once you get up to the intermediate scale, and when you get to the biggest scale of paper, it could be wrong by 3 millimetres in any dimension. Well, who introduced this curious scaling ratio? It's this square root of 2 ratio for paper cutting. It's sometimes called the Lichtenberg ratio. Georg Lichtenberg was a German sort of scientist and mathematician and general man of affairs, who wrote in a letter in 1786 about the sort of advantages which I've just mentioned of having a square root of 2 paper size ratio. Before then, people used a whole variety of different choices. We'll see later there's pretty numbers like the golden ratio that people thought might be a good idea for almost sort of mystical reasons. Here's a little cartoon of Lichtenberg, and he was famous at the time for rather pithy quotations and remarks. And here's one that I noticed in his biography: "Love is blind, but marriage restores its sight." Well, let's have a look at some tables of numbers at these paper series ratios, and then we're going to have a look at some of the hidden ratios and numbers that sit amongst them. Here's the same picture again, showing these paper sizes that we start by halving our A0. Okay, we make the A1 and then we halve again to make the A2. Also shown on here are two rather peculiar paper sizes used in America, which we will return to later on, that are sometimes just called US letter or US legal. And they don't fit into this scheme at all. And that, as we'll see, is something of a disaster. The next series of paper sizes that you may encounter are the so-called B sizes. And these are used for slightly different sorts of objects and leaflets and other types of mailing. And they're constructed from the A series by taking the geometric mean of the two previous A sizes. So B1, for example, is the square root of A1 times A0 in size. And as a word of warning here, I discovered that there's something called the Japanese B paper size, which is really very odd indeed. It doesn't use the geometric mean, it uses the arithmetic mean. So it adds these two together and then divides by 2. Not surprisingly, this is not used internationally and doesn't produce a nice scaling situation of the sizes. Here's what B sizes look like. Here are the dimensions. Again, you go from B0 all the way down to B10. Well, what's all this got to do with Xerox machines? Well, you can probably have some suspicion that the nice point about this setup is that if you look at the series of enlargements and reductions that you're going to get, say, in A series paper or B series paper, or moving across from A to B, then they all change by the same pair of factors. So one is the square root of 2, which is approximately 1.41, and if you go down in size, you're reduced by a factor of 1 over the square root of 2, which is about 0.71. So if you look at what would happen if you made one reduction, okay, you get a size of 71%. If you make 2, you get 1 over the square root of 2, which gets you to 84%. Sorry, I think that's supposed to, yes. And if you then go up square root of 2, 119%. If you just have an enlargement by root 2, it's 141. So what these correspond to, this is the reduction that takes you from A3 to A4. This would be the one that takes you across from B4 to A4, and this takes you from A4 to B4, or B5 to A4, and this enlargement here, A4 to A3, A5 to A4. Well, what I did yesterday was to go around and look at some of the Xerox machines in our department and take some little photographs here of these panels. So the secretaries who were using them were very surprised. I told them it was my new hobby. I was collecting photographs of Xerox machine panels for the new year. They're rather hard to photograph, as you can guess. But one of the things you learn is that different manufacturers work with different approximations to these numbers. And so now you should be able to understand why these numbers appear. So if you look at the top one here, there's 141%. Okay, so that's a magnification by a factor of 1.41, okay, which is the square root of 2. So this is our aspect ratio, which takes you from A4 to A3, or it also takes you from A5 to A4. So if you move from one member of the A series paper to the next lower number, you will have an enlargement by that amount. Across here, you've got very hard to see here, so I think we've got 71% here. So this is a reduction, okay, from A3 to A4. So this is this 0.71, it's 1 over the square root of 2. If you apply it twice, okay, then the square root of 2, it's very close to 0.5. Okay, it's been written as exactly 50% here. This machine here plays fast and loose with these numbers. It can't be bothered to tell you it's 71%, it just rounds to 70%. So 0.7 is its estimate of 1 over the square root of 2. It sticks with 50% for the two reductions, and then at the bottom you've got 25 as the other one. One of the things you learn about Xerox machines from this picture, okay, is that if you were to put in the Xerox machine an A3 document, okay, and you make a reduction of it, then the reduction factor, the 0.71, produces a scaled document which exactly prints out onto the A4 paper. So you don't need to have all sorts of different paper trays to deal with reductions from one type of paper to another. So the rationality of the system is in the reduction and enlargement process, you don't create awkward spare margins which are left over at the edge when you move from one of these types of paper to any of the others. So that's the beauty of the scaling relationship, and that's why it's been chosen. Well, here's the sort of the grand picture, as it were. I've just done it for the A-type paper. So if you want to go from A0 down to any of these smaller types of paper, this is the amount of reduction that you've got to apply. So A1, for example, is 71% of A0, so that's 1 over the square root of 2. If you apply another reduction, so you multiply 0.71 by 0.71, you get 0.504. So that's why A0 to A2 is 50%, roughly. If you apply another reduction, so you multiply by 0.71 again, you're down at 0.3579, really 36%. In this manual, it's called 35. Multiplied by another 1 over the square root of 2, and you're down to 0.25, 25%. So all these numbers along this row, which are taking you to successively smaller A sizes of paper, are all just multiplications by 1 over the square root of 2, although they've been rounded up to rather disguise this fact. If you go in the other direction, okay, then you can see if you divide by 0.71, you go up to 140, okay, 198, 279, 396. So these are some of these larger numbers along these rows. So the whole of this vast table of relationships between paper sizes is simply a multiplication or a division by the square root of 2 in any direction. And you can see this 396.8, 396%, it's rounded to 400. The 279, if you can see it, has got rounded, in fact, to 283. It's a particularly bad approximation. And this 198 gets rounded to 200. Newspapers are an interesting case. If you're old enough, you probably remember the extraordinary Sunday Sport. I I think there's now a sort of an annual calendar of the front pages of the Sunday Sport. I can remember being rung up by the editor of the Sunday Sport with a cosmology story that they had, and they wanted to know if it was true that the universe would once have fitted inside a matchbox when it was extremely young during the Big Bang Theory. And I told him, oh, it was much, much smaller than that. And he said, no, I think a matchbox is about the smallest that any of our readers can really envisage. This was a particularly brilliant story because the following week the headline was, World War II bomber vanished from the surface of the moon. So, and then when they asked Patrick Moore by phone what he thought of this, the next story, which was astronomers had discovered heaven, they quoted him directly, "This is the most fantastic thing I've ever heard in my life." Well, there are typically three types of paper size that get used for newspapers. The large broadsheet, okay, which was introduced in the early 1700s, I think about 1712. And the reason it's so big is there was a tax on the number of pages in newspapers. So if you had big pages, you paid less tax. There's then the tabloid. The quality dailies, when they produced tabloids, didn't call them tabloids for these sorts of reasons. They called them compact edition. But they're exactly the same in size, not in content. And then there's a European size, which is known as Berliner, which is familiar from things like Le Monde, although unfortunately not the Berliner Zeitung. It doesn't use this format. Well, this is part of the last part, really, of the paper size saga, that just as you could create a B size from A size, you can create a C size by taking the geometric mean of the A and the B size. So C1 is the square root of A1 times B1. Well, why would you do this? This rather beautifully creates a series of paper sizes which are the sizes of the envelopes in which the A or the B series papers will nicely fit. So here are the numbers for what they're worth, but the idea is, for example, that a C4 envelope holds an A4 letter very neatly, okay, unfolded. And you can see from the actual dimensions, here was A4, okay, 297 millimeters, and it's fitting in 324, 229, as opposed to 210. So it fits in quite nicely, and if you go up to C5, then when you fold the A4 in half, it also fits just nicely inside with a little bit over. So there's a logic to this new series of paper sizes. They're just designed really for envelopes. So remember, the CN envelope holds the AN letter unfolded, whereas the CN envelope holds the AN-1 letter folded in half. Okay. And you can work out for yourself, if you wanted to fold it in 4, you go 2 C series sizes down. So folding your A4 letter twice produces a size that fits nicely inside the C6 envelope. So study this carefully, and you too can become the Regius Professor of Envelope Science at Oxford. We don't have such things at Cambridge. Well, here's a little summary of the sort of uses for these types of paper. We've seen the A series. We're familiar with technical drawings and posters, articles, scientific papers, and so forth. So we all tend to work with these with A4 most commonly. Once you start cutting the A4 sizes in half, you're down to notepads. There seemed to be a rumour around, I don't know whether it was just created by the English, that A6 is used for European toilet paper. I measured our toilet paper at home, which came from Waitrose or somewhere, and it is not A6, so it is different to these paper sizes entirely. A6 is postcard size, regular postcard. Okay? So you can fit it inside a C6 envelope if you want to put a postcard in an envelope. Books are where you find great use of the B series and also these higher number A and A-series things. Envelopes we've seen already. The newspaper sizes, okay, B4, A3, we've just seen. The very small ones with the high numbers, playing cards is the commonest application. So there's a sort of hierarchy of interesting uses. If you want to carry around a formula in your wallet for what the size of these things is, okay, the fact that at each, as you move up to the next n size, you reduce by another factor of the square root of 2 means that these are the actual sizes of these pieces of paper in meters. Okay, so A1 is 2 to the power minus a quarter minus a half. A2 would be 2 to the minus a quarter minus 1, and so on. If you multiply them together, you notice that things become rather simple, because the width times the height gives you the area of these pieces of paper. So the area of AN is, this cancels out, it's 2 to the minus n. Okay? So the area of A0, it's 1 by 1, okay? And as you go up the series, A1, areas are half as small, 1 over, and so on. Amusing little digression, okay, if we were to go to some hypothetical and completely enormous value of n that's impractical, let's go to A233. Suppose you could make something that had the size of a piece of A233 paper. It's not many reductions, really. It's just 233 goes with the reducing Xerox to show you how quickly things get small when you keep halving them. The area of this piece of paper would be 2 to the minus 233 square metres, which is 10 to the minus 35 a metre squared, which is the smallest physical area that we can contemplate in modern physics, something known as the Planck area. It's the scale of size over which the known laws of gravitation and quantum theory both break down and have to be replaced by a new theory of quantum gravity. So this is sometimes called the Planck unit of area, and it's defined by Newton's gravitation constant, Planck's quantum constant, divided by the speed of light cubed. So it's a dimension of area that's defined by the fundamental constants of nature, not by some human choice. And one of the great discoveries of modern particle physics and string theory and black hole physics is that fundamental structures in nature, indeed maybe the whole universe itself, has an entropy which is defined by the surface area. So all the information is in the surface area, not the volume or the mass. And that entropy is proportional to the surface area in Planck area units. So the whole universe has got a surface area of 10 to the 120 in Planck area units. And this is sometimes known as the Bekenstein-Hawking entropy. So you could work out that the Bekenstein-Hawking entropy of a piece of A233 paper is 1. Okay. And you can work out what it would be for a piece of A4 paper. It's very, very small in a sense compared with the entropy of the whole universe, as you might expect. Well, this business about area is, again, of great practical use and shows, again, how someone like Lichtenberg had thought rather carefully about why you want to introduce this type of paper system with this aspect ratio. So as I just said, A0 has got an area of 1 square metre, so A4 has got an area of 1 over 2 to the power 4 square metres, which is a 16th of a square metre. A1, it would be half a square metre. And from this you can work out what will be the weight of a stack or a quantity of paper of any size, very simply. Ordinary paper, the sort that you write upon, if you collect stamps or make exhibition mountings, you'll use much higher quality paper. But ordinary paper, which you use to leave note out for the milkman, probably has the standard paper quality of a weight of 5 grams for each page of A4. So you can see, knowing this, you can work out what the weight is of any particular piece of A-series paper, and if you have a stack, you can very easily work out the weight. Well, let's tell you something that you can stay away and make use of. The C4 envelope, okay, weighs a bit less than 20 grams. And so you can work out how many sheets of A4 could you put in it before you tip the scales and go above the post office's 100-gram limit for your letter at a particular first-class or second-class rate. Well, you can see if you have 16 pages at 5 gram a page plus 20 for the envelope, that's 100 grams. So this is a good rule of thumb. You can put 16 sheets in that envelope, in that C4 envelope, before you go over the limit. So more generally, if you look at a whole stack of papers of any A series or B series, you can very easily work out the weight just by knowing the standard weight per sheet. So it's why sometimes you see paper quality is just described as a weight. So someone will say this is a 100-gram paper. Sounds a bit odd. What it means is that that's the weight of the standard area of that paper. Another rather neat feature of these scalings is that if you're a technical draftsman and you had made a drawing on a piece of, say, A3 paper, and the drawing is then reduced to A4, and you wanted then to amend the drawing, or somebody wanted to add something to the drawing, if you tried to use the same pen, the nib size would be too big and the amendments would stick out and look peculiar. Well, draftsmen have thought of that, and if you go down to your local branch of Staples or wherever you buy pens and technical drawing equipment from, you'll find that there's a group of standard sizes sitting on the shelf of technical drawing pen nibs. And the standard sizes may be 2 millimeters, 1.4, 1, 0.7, 0.5, and so on. You're probably also already recognizing a certain pattern here. Okay, square root of 2, okay, 1 over the square root of 2, 1 over the square root of 2 times 1 over the square root of 2. It's exactly the same sequence. So the sizes of technical drawing nibs have been chosen so that they scale also in the same way as the paper sizes. That to go up the scale to larger nibs, you multiply by the square root of 2. To go down to the next smaller size, you divide by the square root of 2. So the consequence of this, when you look in practice, big companies like Castell tend to have standardized around just 4 choices. So in a mass marketing shop, you'll find just 4, and they colour code them white, yellow, red and blue so that you can easily recognise them. So they're just 4 of these choices. So the trick is that if you draw on a piece of A3 paper with the 35mm pen, and then you reduce the drawing to A4, you can carry on drawing on that piece of paper using the 25mm pen, and the 35mm lines will have been reduced to the size of the 25mm lines. So to add your drawing, you adjust your lines to the drawing after it's been reduced or it's been enlarged. You just use the smaller or the next larger pen in the technical drawing series. And if you look at stencils, you have exactly the same type of structure. So stencils, you're looking both at the thickness and at the height and width of the letter. So the series of stencil sizes, okay, follows the same pattern. So if you use the next size of stencil up, you will be able to use that. You'll be able to use that on the next larger magnified paper. If you use the next stencil down, it will look like the reduced size copy of the previous document. So most people are not aware of this sort of thing unless they do technical drawing professionally, but there's a rationality to the sizes of the nibs, the size of the stencils, and it's locked to that square root of 2 aspect ratio, just like the paper sizes. Well, I mentioned American paper sizes. This is one of these things that you really just want to draw a horrible curtain across and forget about it. If you want real irrationality, then American paper sizes, which there's only 3 countries in the world that don't use the paper size aspect ratios I've been talking about so far, the so-called international standard, and those countries are the USA, Canada and Mexico. And they use a curious collection of historically somewhat ad hoc paper sizes. The commonest ones in America are called letter, legal, which is not used for legal documents, by the way, executive, which doesn't tend to be used by executives, and something called leisure or tabloid. And they don't have this scaling aspect ratio. So when you go to the United States and you use the Xerox machine for the first time, you have a horrible shock. Because if you take a piece of large paper, which you sort of fondly imagine is a bit like A3, and you make a reduced copy, okay, or suppose you start with 2 sheets of A4, you put it on the Xerox and you're going to make a copy which is going to have the 2 on 1, you find there's a great big margin has been created on each side. So there's not a coherent scaling between the different sizes of paper, that if you want to end up with a result that we're familiar with here, you would have to introduce new paper trays with different sizes of paper at each stage. So you don't have a situation where 2 pieces of A4 side by side produce a reduced copy on a piece of A5 paper. So if you're interacting at a business level with Americans and they're sending you documents that you then want to Xerox and distribute, they all end up looking rather ugly. And exactly the same problem exists for lettering sizes, for stencils, and for technical drawings. Well, the next type of ratio I want to talk about a little is the so-called golden ratio, about which many mystical things have been written. You notice that we don't use the golden ratio for paper sizes. There's no reason why we would want to. The golden ratio has a long history. People were attracted to it aesthetically. It's used greatly in art, perspective, in sculpture. People associate all sorts of mystical significances to it. We've encountered it already in this course when we looked at continued fractions before Christmas. The golden ratio had a most remarkable continued fraction expansion. It was farthest away from any rational number. So it's the irrational number that's farthest away from any rational number, that's the worst approximated by rational numbers. Well, what is it? Suppose that you have a shape here. We'll draw it as an oblong. We'll say that the width is 1 unit and the height is going to be something else, which we'll call phi. And one traditional construction is, suppose that you take out a square from the top. So that's got side lengths 1 and 1. Then what's left will be of side length phi minus 1, and the width is 1. And we want to have one of these aspect ratios again, so that the ratio of the height to the width of this object is the same as the ratio of this side, okay, this side to that side, the bit that's cut off. So phi over 1 is 1 over phi minus 1. Well, if we multiply up by phi minus 1, we get this little quadratic equation that we saw before in the December lecture. It's a quadratic equation. We can solve it straightforwardly, and phi is equal to half times 1 plus the square root of 5. So it's clearly an irrational number. If you know what an algebraic number is, it's an algebraic number because it's the solution of an algebraic equation. If we put in what the square root of 5 is, first decimal places, it's about 1.618. Okay, so this is the famous golden ratio. Sometimes come across its reciprocal, 1 over phi, which by dividing by phi here, we get phi minus 1 over phi is 0. So 1 over phi is just phi minus 1. And it's 0.618. Okay, so this is 0.618. Okay, that's 1. And this is 1.618. So this is the golden ratio. The aesthetic interest in it was always that somehow this is the most appealing shape to us aesthetically. Once people start looking into this, there's not very much evidence for it. What looking into it would mean is giving people a lot of oblong shapes and saying, which one do you like the most? You know, which, or if you ask someone just to draw a rectangle, which is the one that they tend to draw? And on its side, the claim would be that this one, where this is 1.618, okay, this would be the sort of the golden rectangle. And if you look far enough, you can find people that do indeed draw rectangles a bit like that. Euclid had a slightly different definition. It's an extremely old one, 300 BC, and it's worth seeing it. He doesn't use rectangles and areas, he just uses a line. And phi is the distance from A to C, and 1 is the distance from C to B. And phi is to be the ratio of A to C divided by C to B, when that's also equal to A to B divided by A to C. So when is AC over CB equal to AB over AC? And if we call this phi, then this will be phi plus 1 over phi, and we have exactly the same formula. So phi is just the ratio of this to this, when it's equal to the ratio of that to that. The golden ratio has all sorts of rather remarkable mathematical definitions and properties. One that we saw in the December lecture was that if we expand it as a continued fraction, then this staircase has ones all the way down. So once you look at it in the form of a continued fraction, its extraordinary and symmetrical properties become remarkably evident. So you might have wondered, you know, why on earth would people regard this as being so magical and profound and significant? It just looks like any other old decimal. 1.618, so what? Happens to be the solution of this funny quadratic equation, so what? But once you start looking at it as a continued fraction, it clearly is uniquely specified and rather remarkable. You can also write it as a continued surd, the square root of 1 plus the square root of 1 plus the square root, and so on. And again, all the entries are ones. So it does indeed have these very remarkable properties. And as I mentioned just now, it's in some sense the most irrational number, because it's farthest away from any other rational number. There are amusing but extremely accurate simple approximations that people have hit upon for this, that it's roughly the square root of 5 pi over 6, and even more interestingly, it's roughly 7 pi over 5e. And these are approximations that are amazingly accurate. So they're accurate to a few parts in 100,000. And of course, people try to find some deep mystical reason for these approximations, but they are in a sense just coincidences, okay, but very good ones. If we look at that continued fraction expansion of the golden ratio with all the ones in it, then what we can do, remember, we can cut off the continued fraction expansion at each step and work out what the rational approximation is to phi. Well, if we just take the first one, we get 1. If we take the next one, we get 1 plus 1 over 1. Take the next one, it's 1 plus 1 over 1 plus 1 over plus 1, and so on. And if we just round these up, first approximation is 1 over 1, next one is 2 over 1, the next one is 3 over 2, 5 over 3, 8 over 5, 13 over 5. These are rather remarkable, because each number you'll see appearing here is one of the Fibonacci numbers. So the Fibonacci sequence is 1, 1, 2, 3, 5, 8, 13. So you make each number by adding the previous two together. Start off with 1, 1, and then it's 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, 8 plus 5 is 13, and so on forever. And you see this is how we are arriving at the numbers in this rational approximation sequence. Every one of them is a Fibonacci number divided by the previous Fibonacci number. So you begin to see again why people think that there was something rather magical about this number. Well, the places where one starts to find people using this number in interesting ways in creating paper sizes and documents and artistic creations, besides in ancient times, particularly in medieval times. And we're going to finish today just by looking at a few examples of what you might see as the medieval counterpart of deciding on paper sizes today for Xerox machines. And the problem is of making, first of all, books and then designing book pages. If you're making paper, making a book in medieval times, you're going to create a group, or what might be called a choir of pages, which will then be sewn into a book together. And you'll make those from one very large sheet of paper. And a way you might do this, okay, you might do it for paper later on, or parchment, or more commonly from vellum, which has different texture on its two sides. So one side of the vellum will be fleshy, and the other side will be rather hairy. So you actually have some worry about what the facing pages might look like. So how do you go about making your paper sizes? Well, you start off perhaps with a big piece of paper like this. You know, one side is one colour and one is a different size of colour. And you first of all would fold it in half, okay, like in the first frame here, and this is called folio. Okay, so remember the Folio Society, you now know why. Okay, so just folding paper down the middle produces this folio size. What you do next, okay, is then to fold in that direction, okay, and then to fold again in the first way. And you've now got what's called quarto, because there are 4 thicknesses of paper, okay. If I did the whole thing again, okay, folding down and then across, I would end up with 8 thicknesses of paper, and that's called octavo. I'm not going to do that because it's getting a bit small. So at this stage, if I do what you do in the library when you consult books that nobody's ever bothered to look at for hundreds of years, you use your paper knife, okay, and you cut all these pages along the folds, okay, then we get one which I did earlier. So I cut all these earlier, and what you end up with is rather elegant, because on the outside, okay, you've got 2 white pages. When you go inside, you've got colour facing colour. You turn over, you've got white facing white. You go over, you've got colour facing colour. And so on forever, as it were. And if you've done the same with the octavo, folded again, have exactly the same pattern. So this simple folding rule ensured that if your book was made of vellum, for example, you would end up with 2 fleshy pages facing each other here, 2 hairy pages facing each other there, 2 fleshy, and so on. So it's a very simple rule, and it doesn't matter how many times you carry it out, you will end up with this rather elegant and simple structure. Well, paper layout is an interesting problem. You may not have noticed if you spend much time gazing at ancient books. Here's one that I think I showed in my very first lecture of the year. It's Adelard's edition of Euclid in Latin, and this is hand inscribed. There's no diagrams really then these have been added by the reader, I think, for himself. In the margins, they're not really integral to the text. So it's a book of geometry, theorems and proofs, and the different paragraph headings show you that when a theorem is being announced, use slightly bigger text to state the theorem, and then smaller text, you've got the proof. Now, when you look at this, you notice that it's set out in a rather beautiful way, but it's not a random way. So you notice the differences in the margin size at the top, and the centre at the top, the outer, and the lower. And a counterpart, in a way, of our modern deliberations about convenient paper sizes are the structures of these margins compared with the size of the page. Here's a printed Gutenberg Bible. You see the same type of considerations here, this very large bottom margin, the centre, the top, and the outer. They're the same as in the previous book, I think, to high accuracy, and they're certainly not random. So what's going on here, this so-called medieval book page canon of rules about how you lay out a page, how you create margins. And sometimes people use the golden ratio in some of these volumes, but it wasn't really common. The commonest was a very convenient type of layout, which used a ratio of 2 to 3. So this picture here shows here's the text area, here's the page area. And the nice choice was to choose the proportions of the inner to the top to the outer to the bottom in proportions 2 to 3 to 4 to 6. And this is a geometrical instruction. We'll see another one in a moment. It's a bit clearer about how you arrive at that. And you get this when the page proportion is in the ratio of 2 to 3. More generally, if you made the page proportion ratio 1 to R, then these margin ratios would go 1 to R to 2 to 2R. And so this case is when R is 3 halves, and this has the rather neat property that the height of the text area is equal to the width of the page. Okay? So these are the sort of medieval counterparts of the considerations of our paper sizes. And here's a construction that Tishkold had reconstructed and claimed was the way people tended to do this in ancient books, or how easy it would be to do it if you wanted to do it systematically. So here's your double page, and suppose here you divide up the width in 1/9 units of the page width, and then you divide the height into 9ths as well. They'll be rather bigger grid squares. And then what you can do by drawing this diagonal across to the corner of the page, and this diagonal here, and then the hypotenuse, okay, you can construct this rectangle over here, like that one. The centre of this circle allows you to draw a circle which touches, okay, so its diameter is the page width, and its diameter is therefore a way to work out the text height to make sure it's the same as the page width. So the scalings that you have, because this is 1/9 of the height, this is 1/9 of the width, this guarantees that you have 2/9 over here, 1/9 here, 2/9 at the bottom, 1/9 at the top. So it's a simple, rough and ready way on your double sheet of paper to make sure that you've got the grid size, the text area rightly laid out. And you can work out rather simply from these ratios what is the ratio of the page area to the text area. And it's just 3/2 squared. So 9/4. So it's not terribly efficient, but probably when you look at these pages, you agree that they have a certain appeal. Okay, there's something aesthetically rather nice about the way in which they've been laid out. And pretty much all the books that you look at of this classic sort have this type of scaling ratio, unless there's some other reason to enlarge a margin to have diagrams or other notes or index footnotes or something like that. So I hope I've given you some taste for the way in which both today and in ancient times people worry about paper sizes, paper layout, and next time you copy something on the Xerox machine, remember there's a reason why it tells you 0.70 or 0.71 or 141%, so you've got to think root 2 or 1 over root 2, okay? And the next time you look at ancient manuscripts or books in the library, there are no doubt one or two up here perhaps hidden away on display, notice that the layout of these books is just not random. There's a mathematical scaling and geometrical construction sitting in the background that became habitual for the people who then inscribed their rather beautiful calligraphy onto those pages of vellum or paper. Thank you.